Well, welcome to our May meeting. So let's get on with our meeting. It will be led by Thomas Williamson, and also speaking will be Chao Wang. So let me turn things over to Thomas, and we'll get started.
Well, thanks to everybody or thanks for the invitation to be with you today and to present some of the work that we've been doing based on the i-HMBC experiment developed at Merck. And we have the original true inventor, Zhao Wang, with us today to expand on the experiment. And so hopefully everybody can take something away from us today or take something away from this presentation that they can use in the lab on their everyday work. So I think it goes without saying that one of the most important NMR experiments for structure elucidation is the HMBC type experiments. These are very complementary to HSQC and then, of course, our 1D proton and carbon data. But the issue that the longstanding problem with HMBC type experiments is that it's difficult to disambiguate two bond correlations versus three bond or further correlations. And so a lot of people have been thinking about this for a long time, and there have been a number of different approaches to this, some using cozy type correlations for systems where we have protonated carbons in the for the two bond HMBC spot. And when we don't have protonated carbons in that location, we've opted for things like the 1-1 adequate type experiments. And these experiments are very powerful and provide us a really nice um, option for determining exactly what would be sort of equivalent to a two-bond HMBC correlation, looking at the magnetization transferred from a proton to a carbon and then a neighboring C13 molecule or C13 atom, I'm sorry. And then so basically, the issue with this is that, of course, the sensitivity is very low for these. We're looking at one in every 10,000. C13 nuclei has a neighbor in C13 nuclei. And so the inverse detection helps. We can use things like non-uniform sampling to help. But ultimately, it takes a long time to acquire these data, but when you need it, it can really help. And I think it was a huge breakthrough back in the I guess mid 90s, 1995, 1996, when Bernd Reif originally proposed the adequate experiment, and it was demonstrated by Bill Finnickel's lab on a marine natural product, where they were able to get what was considered good data on about 14 milligrams of this marine natural product over the course of a weekend or so. And so this has sort of started gaining some traction, gaining some attention. And there have been a lot of different iterations of improvement to the adequate experiment. This particular one here incorporates many of those um, developments, including the homonuclear bird-based decoupling developed at Gareth Morris's group, and Tango preparation period to help eliminate any residual magnetization and minimize artifacts from that origin. And so, still, this leaves a lot to be desired, although it can help or does help collapse these multiplets and increase our signal to noise. That's normally the ones that we worry about the most are our multiplets, our CH protons in particular, where they tend to be highly coupled. And if we can actually collapse those, then we can gain a significant increase in signal to noise. Here we show example in ibuprofen where we see a 67% increase in signal to noise for that signal to noise limiting response. So this is really sort of a big deal, helped a lot, and was eventually used to correct the structure of cryptospirolepine. This is sort of the first example of this type of experiment being used on a sub-milligram sample of any molecule, and in this case, it was a natural product that had been reported decades before and been referenced dozens of times in the literature. And finally, using this experiment, we're able to disambiguate that and determine exactly what the correct structure was. So this was all great, but this came at great expense, I guess you'd say. This is a 1.7 millimeter micro cryoprobe at 600 megahertz, and we happened to have a long weekend available that we were able to set these experiments up, the one HD adequate and one N HD adequate. And so, it's just sort of a fortuitous set of circumstances that allowed us to acquire these data. It's not something that you would use in your sort of everyday routine work if you didn't have to. A little while later in 2018, Ole Sorensen and Katalin Kover actually published what appeared to be another groundbreaking sort of incremental improvement in determination of or distinguishing the differentiation of two bond and three bond multiple bond correlations. And this experiment was called the SEA-XLOC experiment. And I won't really go into a lot of technical detail about it, but it's pretty interesting and that allows us to selectively isolate our zero quantum and double quantum coherence and manipulate it in such a way that we can either see a tilt for our two bond or longer correlations or see the complementary sets of data. And I'll demonstrate that here in a moment. But in our case, we actually ran across a paper from one of our good friend and collaborators, Nick Oberles at UNC Greensboro, and they had actually dived into a study on the limitations of DFT calculations for the determination of relative configuration. And in the case of these bis-lactone macrocycles, they basically said that using the sort of conventional approach to DFT, um, they were only able to assign two out of the three stereo centers, and so we sort of looked at this as a good friendly competition and challenge accepted, and so we decided to take this project on and see how far we could push it. And we thought at first this was going to be pretty easy, and we didn't really anticipate any big problems. But it turns out that in fact, whenever we did start to do some conformational analysis and subsequent DFT calculations on this molecule, we saw that we got sort of conflicting results for our proton and carbon chemical shifts, and then also with our anisotropic analysis, we found that our singular value decomposition was unstable, and sort of all of these results sort of pointed to the fact that our populations, our conformational populations, weren't really representative of reality, right? So we have very minimal energy differences between the different conformations. So it was quite difficult to come up with an accurate Boltzmann population for this molecule. So we decided to take an approach where we would use a whoops, sorry. Decided to take an approach where we would use our scalar coupling constants to use as a filter. So basically, like a J sampling type approach where we would use the scalar coupling constants to constrain or restrain or limit our selection process for our conformational analysis. But in order to do that, we actually needed to disambiguate some of these assignments, and two of the one of the main cases that we needed to do this were these two protons, these two methylene carbons here between these two carbonyls. And these two could be assigned either way. They were fairly similar in chemical shift. So in order for us to be able to use those data in the selection of is actually which. And so we looked at this CX-LOC experiment to carry this out. And as you can see here, basically the idea is that we basically take our zero quantum and double quantum magnetization and manipulate it in such a way that we can use our passive and active couplings to sort of introduce a tilt for our desired correlation, whether it be the two-bond correlation or the longer range correlation. In order for this to work, we actually need to have some sort of multiplet structure on the protons of interest so that we can actually observe this tilt. And it's not exactly straightforward type of analysis. Once you get the hang of it, it's okay, but it's not something that everybody in the walk up NMR is going to be able to go up and just use this type of data. So it also can be quite confusing because depending on how you set up the data or set up the experiment, the data are completely complementary to each other. So you need to be careful about which type of selection you've actually done in the experimental setup. But here's a sort of example of the real data, and you can see that when it works nicely. You see this tilt, which distinguishes the two-bond correlation in this case. And then when we select for zero quantum magnetization, we can see that it basically reverses it. We see the tilt in the complementary way. So this works pretty nicely, but as I mentioned, it does require that the multiplet of interest has some sort of tilt or some sort of multiplicity to it so we can observe that tilt. Then it doesn't really work very well. Supposedly we could determine it through looking at the line width and all that, but it's pretty ambiguous when you get to that stage. So it still left a lot to be desired, but in our case, it actually worked and allowed us to select the conformers that were relevant to our analysis. And you can see here that once we had done that, then our proton and carbon chemical shifts that were calculated all agreed were pointed to the same diastereomer. Our scalar coupling constants, our proton, two-bond, and three-bond coupling constants, our two-bond and three-bond um, uh, um, uh, proton and carbon coupling constants, and our anisotropic data all pointed to the same conformer. And so we're able to reliably, confidently, and I think unequivocally assign this as diastereomer 1A. So we're very happy that it solved the problem, but clearly this wasn't a one size fits all type of experiment. And we wondered what would happen in the next case whenever we ran into such a problem. Along these times, we were sort of working on some fluorine detected experiments, looking at fluorine detection of carbon-carbon connectivity, C13 connectivity. So basically like a fluorine detected adequate type experiment. And in this case, you can actually see substantial isotopic shifts here. And you can actually see in the F2 dimension that these correlations don't really line up. And then as you can actually see in the HMBC data, it's even more apparent where we could actually use these isotopic shifts to discriminate between the two bond, the one bond, and then of course the three bond or longer correlations. And so this was actually pretty exciting. We were excited about it in the context of fluorine NMR, but hindsight's 2020, and at the time, most of us working on this project hadn't really considered its application to carbon. But Zhao Wang here at Merck, he basically had that aha moment and basically thought, well, if this works for fluorine, why can't it work for carbon? And in fact, actually does do the same thing. And basically, he went on to show that for the two bond HMBC type correlation, we should see an isotope shift, which would be considerably larger than the isotope shift that one would expect from a three bond or longer HMBC correlation, which would be basically non-existent. And so this is just a figure copied from their original Nature Communications paper, and you can see if you sort of put on your glasses and look hard, you can actually see how these chemical shift of these protons are lined up or not lined up exactly right. And this is due to the isotope shift. And if we go through here and we look at these very carefully and measure them very carefully, then what we can see is that there's a sort of a dividing line between upfield isotope shift of about negative 0.5 ppb for two bond proton carbon correlations and something less than that for all of our three bond or larger HMBC type correlations. And so you can see here, even though these shifts are quite small, with the appropriate amount of digitization, we can actually see that they are measurable and they do follow a very nice striking trend where we only see maybe one exception out of all of these couplings that were observed, or all of these isotope shifts that were observed. So um, really was demonstrated on a whole suite of natural products, including some just spectacularly complex molecules like calicheamycin and others. And in all cases, it was shown that these structures could have been solved quite easily and at least in a straightforward manner through the use of this experiment. And so, not too long after this work was published, our group actually ran across an issue where a compound named portamine B that had been reported from some co-workers um, in the past was actually shown to be wrong or had been incorrectly assigned. And Phil Barron had actually shown this in some synthetic work on portamine A, which shows some just fantastic anti-cancer activity. So it'll be interesting to see where that molecule goes. But on the way to the synthesis of portamine A, one of the intermediates was in fact portamine B. And basically, Phil, we had some communication with him, and sort of he told us what he knew about it. And although it was clear that the original structure of portamine B was incorrect, which was basically originally reported as this sort of open ring system here, where you can see this tetrahydrofuran ring had opened up. He had revised that structure just based on the synthetic work, but hadn't really considered how the structure was misassigned or really gone back and done any type of adjudication at all to try to figure out what happened and sort of get to the bottom of the mystery. And so these are kinds of problems that we really like. And so it turns out that we actually had to produce an organism for portamine B, and Phil was nice enough to share a small amount of portamine B from his synthetic work with us. And so we actually decided to take a close look at this, and at first it seemed rather odd. It seemed like we were actually getting some conflicting data because not only did portamine B show the addition of an extra oxygen in the mass spec, just as in the original structure, you can see here we actually add a hydroxy group. But it eluded before the portamine A on the reverse phase column. And so the difference between these structures is this ketone versus hydroxy group. And so you can imagine that in the revised structure of portamine B, where we have the ketone, we'd expect it to elute after portamine A. And so we had two issues that really didn't make sense. Um, and so we just started looking at it a little bit closer, and we went back and found some of the original data. And you can see here for portamine A, we do see a nice clear HMBC type correlation across that tetrahydrofuran ring. I'm sorry, in this ring right here. And then in portamine B, we in fact did not observe that HMBC type correlation. And that was another thing that had sort of led to the original misassignment. So we had three pieces of data, which all are in support of the incorrectly assigned molecule, and really no data that's in support of the new revised structure. And so we were really puzzled about this and decided to look at it more carefully. And one of the first things that we did is incorporated the new Delta 50 methodology for calculation of proton and carbon chemical shifts, in this case in chloroform, um, and comparing those to our experimental values. And Delta 50 basically is based on benchmarking set of 50 compounds, which represent a wide array of chemical functionality without complications due to conformational flexibility or a lot of hydrogen bonding type situations. And so turns out it works really, really nicely, and in our hands at least, when compared to virtually all other types of DFT approaches, we see that Delta 50 generally outperforms all of these. So if you haven't checked it out, I highly recommend it. It's a nice open access article, and we're really proud of this, and think that that could be useful in your work. So check it out. But anyway, when we did these calculations, it's kind of hard to see all these data. But at the end of the day, I guess the main thing to point out is that both our proton and carbon data were the first supporting data that we had for the revised structure, and they clearly agreed better with the revised structure than with the original proton and carbon data. So sort of added a lot of credence to the revised structure. And so now we finally had a good set of evidence that's just, actually in support of that revised structure. And we still had the three sets of data that were sort of posed against the new structure. And so we decided to incorporate this isotope i-HMBC experiment to use our isotope shifts to differentiate the 2-bond versus 3-bond correlations. And as we sort of thought about this structural problem more and more, we considered that in the HPLC, there's actually presence of formic acid in that solvent system. And so we've got this tetrahydrofuran ring here in acidic media. And so if we thought about things that we could make when we do that, we could actually form this hydrate or this imine gem diol structure shown here up top, or we could form a hemiaminal ketone type structure as shown here. And in order to differentiate which one of these was which, we needed to be able to determine which one of these chemical shifts was which. And so basically, is this far downfield ketone 2-bond correlation, and then the next proton further upfield, or exactly what's going on. And so basically what we were able to do is to go and show that if we look at the correlations from HMBC correlations from the protons here, from these methylene protons, we were able to show that the imine gem diol structure was actually the correct one, where basically that 2-bond correlation is represented by the chemical shift here at 107.7. And then in the other structure, we'd actually expected to see the ketone far downfield. So with that, we were able to really confidently assign the structure, and then not only that, but to be able to show that it was actually a reversible situation. And so in the solvent system with the acid, we actually did see the gem diol. So you see the addition of the extra hydroxy group, and we'd expect to see this elute ahead of portamine A. It accounts for the extra oxygen, and all of the chemical shifts made sense. So this was pretty exciting, allowed us to differentiate this and kind of solve this structural puzzle. And so just want to thank the folks that helped with this work. This will be our group here. And then, of course, our folks from Merck. We got Ryan Cohen, Misha Rebark, Zhao, and then you can't see Yunyi because I didn't have a picture. But just wanted to thank them. And then with that, I'll turn this presentation over to Zhao to follow up and tell you a little bit more depth about some applications of this experiment.
Mention our sponsors as always as well. MR Resources, been around for nearly 40 years at this point, and offering virtually any and every sort of repair service, maintenance service that you might need for your Brooker systems, any Brooker systems, Avance 3s, Avance 3s, Avance 3 HDs, Neos, Ultra Shield Plus magnets, Ascend magnets, on and on and on. They're equipped to handle it, quench recovery, system relocations, repairs. They've got also a very, very well equipped probe shop. Can do, once again, literally anything and everything with cryo probes and cryo platforms. Do check them out if you would.
Okay, thanks, Thomas. So, good afternoon, good morning, everyone. So this is Xiao from Merck Structure Elucidation Group. So I'll follow Thomas' story. I'll talk more following up development of the i-HMBC methodology and what we called isotope shift-based MR structure elucidation strategy. So most of the work I'm going to talk of today is mostly done by Yunyi, but she's on maternity leave right now, so I'm present on behalf of her. So just a brief recap of the i-HMBC. So the original purpose to develop i-HMBC methodology was to just aiming for the determination of the two-bond HMBC correlations for proton deficient molecules. So why we are interested in proton deficient molecules, because those are usually contains a lot of quaternary carbons or very rigid caged skeletons, and they are very challenging to solve structures. And we use i-HMBC. Basically, i-HMBC is a regular HMBC just with a longer acquisition time and higher proton, much higher resolution on the proton dimension. So then you can differentiate, you can detect those sub ppb level of tiny isotope shift from C13. And so we demonstrated i-HMBC was a very sensitive and effective method to solve proton deficient molecules, like some structures shown here. But for proton-rich molecules, we don't need i-HMBC or 1,1 adequate, because for proton-rich molecules, cozy most of the time is enough. But by using cozy, we can establish the carbon-carbon connections instead of using the more complicated and less sensitive heteronuclear correlation experiments. But however, just recently we find there's for proton-rich molecules, there's still the structural elucidation sometimes is still not straightforward and unambiguous. It's partly due to some related to coupling constant. So for our traditional structure elucidation workflow we have used for decades, we usually use a series of standard 2D experiments like COSY, HSQC, HMBC to solve the molecular structures. And all these 2D MR experiments are relied on the through-bond couplings between MR active nuclei, and the coupling constants was actually the cornerstone of all these experiments. And just from a practical practical point, to achieve a balance between maximum sensitivity of these 2D experiments and the generality for the substrate scope. So the parameters of these 2D experiments were optimized for the range of the typical coupling constants commonly observed in organic molecules. So these typical coupling constants, this coupling constant range has been extensively studied for decades, and we all have a pretty good sense of between the correlation of the coupling constant, the magnitude of the coupling constant, and the structures. For example, if in a COSY, if we see a strong COSY correlations, that means it's either two-bond geminal proton-proton coupling or adjacent three-bond proton-proton coupling. And for longer range proton-proton coupling, like 4-bond, 5-bond couplings, they are usually less than 2 Hertz and very weak on COSY, or most of the time is unobservable. Similar for HMBC and 1,1 adequate. For HMBC, strong HMBC signals usually indicate it's either 2-bond HMBC or 3-bond HMBC. And for 4-bond and longer range HMBC, the coupling constant is less than 2 Hertz. And for 1-1 adequate, where the sensitivity is really crucial, so usually we set the 1-bond carbon-carbon coupling between 40 and 60 Hertz to maximize the sensitivities. So this strategy of using combination of this coupling constant based NMR experiment is generally highly effective in correctly solving structures of organic compounds. And that's why we use NMR as a major tool for structure elucidation. However, the problem underlying this workflow is that from all these 2D NMR experiments, what we observed is actually the coupling constant. All the peak intensity was related to coupling constant and the J-opt you set in the data acquisition parameters. And then we use our experience to translate the coupling constant to the structure information, like whether a strong coupling constant means a short range correlation and a weak signal means related to a longer range correlation, something like that. So this interpretation is the main reason that yields some generate some misassignment of the structures, especially for those compounds that has atypical coupling. That means the coupling constant is out of this common range which we set for our common NMR experiments. So with compound with atypical coupling constant, it will give challenges in both NMR data acquisition and interpretation. And then the misassignment is potentially arise from this. So these are some examples of the compounds has unusual coupling constants, especially in some highly sterically constrained molecules like this. So this first compound is called BCP, or bicyclic 111 cyclopentane. So this is a trending moiety right now. So people use this as a bioester for benzene ring in pharmaceutical drugs, because it in a 3D space, this BCP moieties resembles the steric hindrance steric of phenol ring, but has a better PK/PD properties. So people like to use a substituted BCP moieties in the drugs. And if you look at the proton-proton couplings of these compounds, usually the 4-bond W type coupling is usually less than 2 Hertz. But in BCP, because of this specific geometry alignment between the atoms, you can see there's a 18 Hertz 4-bond proton-proton couplings and the 10 Hertz 4-bond proton-proton couplings from the other protons. So this BCP is unsubstituted, so the protons are equivalent, and the coupling will be degenerated, but the coupling constant still can be calculated by DFT calculations. And I will talk about the BCP later in the talk. And for this cyclobutanol, you see the 4-bond proton coupling is also as high as 5 Hertz. And for aline, there's a large 3 Hertz 5-bond proton-proton coupling, and the 4-bond proton-proton coupling is 7 Hertz. So all these weird coupling constant will give very misleading cozy correlations. And if you are not aware of these structures in priori, then the structure elucidation will be very challenging. And not only proton-proton couplings, all these compounds has also out of range proton-carbon coupling and carbon coupling as well. So all this will give the misleading cozy HMBC and 1-1 adequate correlation. So most of the long-range NMR experiments we are using is not reliable on this type of molecules. And something like BCP and cyclobutane these are some quite extreme examples of the strained molecule that has atypical couplings. But atypical coupling actually exists in a lot more general compounds as well. This is a quite like Thomas mentioned in his talk as well. So this is the original structure was characterized during 1989, and then structure was resolved revised in 2012 by DFT calculations and followed by a confirmation from single crystal X-ray. And in the original structures, this aquatolite structure was proposed to be having this ladder ring moieties, like two fused cyclobutane ring. So the main evidence to propose this structure is based on the observation of this strong coupling between these two proton 2 and proton 10. They have a 7 Hz couplings between them. So naturally, it was assigned as a 3-bond proton-proton coupling. However, if you look at it in the revised real correct structure, this 7 Hz coupling is actually from a 4-bond W-type coupling, but it's a huge number. It's a huge coupling for a W-type coupling. So if you look at the carbon skeleton, the original arrangement is C10, C2, C3, C9. But in the revised structures, the C3 and the C2, these two carbons was switched, become C10, C3, C2, C9. So the C2 is no longer directly connected to C10. And this is a more recent example. This compound is called lomovitazine, and it's a very complicated dimer structure. It's a dimer of a diazo compound. And on this cyclohexenol ring, there's also some sugar substitution group on it. So it's a quite huge small molecules actually, and it's a dimer, like dimerized through the cyclohexenol moieties. So in the original structure elucidation, there was the carbon connection on the cyclohexenol ring was determined by this. So they observed a 4-bond. They observed a weak coupling, like 1 Hz coupling between H2 and H4, and naturally they think this is a 4-bond W coupling. And also the structure was also makes sense because they also observed the i-HMBC from this proton to the diazo carbon. So this is a 3-bond proton carbon correlation. So this actually makes a lot of sense. However, in just a few years ago, this structure was revised by MicroED and some synthetic work from Seth Herzen group. And in the revised structure, so the 1 Hz coupling that originally thought to be a 4-bond W coupling is actually a 3-bond proton-proton coupling. It's just because of the dihedral angle. So this is 1 Hz. And the 3-bond proton carbon coupling observed in i-HMBC is actually a long-range 4-bond proton carbon coupling. So this shows like the challenge during the structure elucidation if you rely on the coupling constant to interpret the bond distance between atoms, because like if you have a small coupling constant, it doesn't necessarily mean it's a long-range coupling. It could be just a short-range coupling, but just due to dihedral angles, it's a small one. And this is really hard to, this kind of mistake is really hard to identify if you don't know the structure in priori. Yeah, so this is the main problem of our traditional structure elucidation group. So what I'm thinking, what we are thinking is like, if there's is there a better solution to solve this problem, like to decouple the coupling constant with the bound range of the correlations. So then the solution is to use isotope shift. So first, isotope shift is absolutely independent of the J coupling because they are coming from completely different like physics meanings. So isotope shift was originated from the harmonic vibrations of chemical bonds. And so because this is originated from vibrations, so the one bond isotope shift is huge because it's directly the bond stretching contributed to the isotope shift. Well, if there are two chemical bonds between two atoms, then the effect of the vibration will be much weaker. And for longer range, it will be weaker and weaker. So the 1-bond isotope shift is always way larger than 2-bond isotope shift. And we also demonstrate that the 2-bond isotope shift is always larger than 3-bond and longer range isotope shift. The difference is small, but there's a like a 0.2 ppm gap between them. 0.2 ppb difference between 2-bond and longer range chemical isotope shift. And for longer range, like 3-bond or 4-bond, 5-bond isotope shifts, they are not zero. And at that range, there's a lot of environment can affect the isotope shift. So 3-bond isotope shift is not necessarily larger than 4-bond or 5-bond, but 2-bond is always larger than 3-bond. So this is the key, and this is the foundation of i-HMBC, like how we differentiate 2-bond correlation versus longer range correlations. And so now we are thinking to use isotope shift to construct the carbon-carbon bond. And for i-HMBC, what we observed is actually a relative isotope shift because of how the experiment was run. So we observed a series of multiple HMBC signals from a single proton, and then we use the most downfield one. Usually that's the long range correlations. We use that one as a reference, and then compare all other HMBC correlations from the same protons, and compare that with the reference to determine the isotope shift difference. So what we observed is the 2-bond isotope shift, the difference between 2-bond and N-bond isotope shift. What we get is a relative isotope shift. The advantage of i-HMBC is that it works for quaternary carbon. And actually, quite some time ago, like Juan Espinosa and the Tiaparella group developed this 1D C13 satellite selective TOXI experiment. So this is a very smart experiment, but it's for proton-rich molecules because it relies on TOXI transfer. So in the proton spectrum, what we see, the chemical shift of HA is the chemical shift of this isotopomer. So all the carbon is C12 because C12 is most abundant. But if carbon B is substituted by a C13 atom, so now the HB on the proton spectrum, HB will show as the C13 satellite, like on the two sides of the main peak of the C12 HB. And if you run a selective TOXI on this HB C13 satellite, and then through the TOXI transfer, you can get the HA, the chemical shift of HA. And this chemical shift of HA is the chemical shift of this C13 substituted isotopomer. So this chemical shift of HA will show a 2-bond isotope shift compared with the HA of the OC12 isotopomers. So what this measured is an absolute isotope shift. So now we have two methods that can reliably measure the isotope shift with sub-ppb accuracy. So this is very important for the analyzing the data. And so next I will show some our real examples in Merck, like how we use this isotope shift based structure elucidation to avoid the misassignment used by from the conventional data analysis and the spectral interpretation. So this is the BCP molecule, and this now is a substituted BCP molecule. So all the protons are non-equivalent right now. And if you look at the coupling is very, very strange. So like 3-bond proton-proton coupling now becomes 0 Hertz. And even geminal coupling, 2-bond geminal proton-proton coupling is only 3 Hertz. But in contrast, the 4-bond proton-proton coupling, the W-type coupling, now is 10 Hertz and 8 Hertz respectively. And for HMBC, there's a 13 Hertz 4-bond proton-carbon coupling. So this 4-bond proton-carbon coupling is much larger than regular 2-bond and 3-bond couplings. And also the 2-bond carbon two-bond carbon-carbon coupling is also 23 Hertz, where it usually should be less than 8 Hertz. So all these weird unusual coupling constant will what they give is a very misleading like 2D NMR spectra. If we look at cozy spectrum, so other than the diagonal signals, so the cross means the peaks we're supposed to see, like the 3-bond proton-proton couplings, but we didn't see, and the circled signals are the correlations that we shouldn't expect to see, or very weak because they are long-range correlations, but actually we see it very strongly in the cozy spectrum. So you can see we are missing a lot of 3-bond proton-proton couplings, and we see very strong long-range 4-bond proton-proton correlations. And also we see some very weak geminal 2-bond proton-proton coupling signals. So if we don't know the structure of the BCP, this cozy is definitely misleading. There's no way you can correlate these cozy correlations to a correct structures. And same thing for 1,1 adequate. So 1,1 adequate for H2, it should see 3 carbons, C1, C3, and C5. But in our 1,1 adequate, we actually see 4 strong signals. There's an additional signal to C4, which is resulted from these large carbon-carbon couplings. So like for these kind of weird molecules, so there's no way to solve the structures just based on the conventional like 2D MR experiments. So then we did the i-HMBC to obtain the isotope shift. So we ran the i-HMBC on the if we look at the i-HMBC signal on the proton 2, this proton sees 5 carbons in the molecules, C1, C3, C5, C4, and C6. Basically, it sees all the carbons in the molecule. And all these are the 5 signals. And these signals has the most downfield proton chemical shift. So we use this signal as the reference. Then we measure the center of all other correlations and compare the chemical shift of all these other signals with these reference signals. And we can see that there are the three signals here, like a singlet type of signals. They all showed quite large isotope shift compared with the reference signals. It's around 0.4 to 0.5. Like 0.2 is usually a threshold between 2-bond versus longer range isotope shift. So we can confidently know that these 3 carbons, these are 2-bond HMBC correlations. And this one is also this one is only 0.1 ppb. So this one is a longer range correlations. So if we map this back, we can see that the 2-bond correlations here are very small, but the 3-bond and 4-bond are much stronger than the 2-bond correlations. So, but if we don't rely on the peak intensity, we can reliably just build the connection from like C2 to C5, C3, and C1, just based on the isotope shift information. And this is a reaction. So we want to run a lithium hydrogen exchange reaction to replace the bromine to lithium and run the following duratization. And to know this lithium hydrogen exchange is successful, we want to quench it with water, and so suppose we should get this product. However, what we got is we didn't get this at all. What we got is another unknown mysterious compound, and like LC-mass show that the butyl group on the butyl lithium actually added to the compound. And based on the cozy HMBC correlations, this one is a very likely structures for the unknown compounds. You can see the cozy correlations shows the spin system from H4, H5, H6, H7, and NH. So this all makes sense. And the HMBC signals from H5 to H6, HMBC correlations from H5 to C6 and H5 to C7 also confirm that the butyl group is on this side of the molecule. However, the problem what we find is that the DFT calculated carbon and proton chemical shift of this molecule doesn't match the experimental data. So there must be something wrong here. Then we try to obtain the isotope shift from the proton 5. So in this case, we tried both i-HMBC and the satellite selective 1D toxic experiment. So because C2 is a quaternary carbon, so the 1D toxic could not get the isotope shift information there. But on the other side, the 1D toxic, what you got is the absolute isotope shift. So you see that the numbers are a little bit different between the two methods, but like the difference between the isotope shift, like the difference between C4 from H5A to C4 and to C6, the difference is 0.39 ppb, and here the difference is also 0.39 ppb. So the relative number is correct. It's just one. What you got from i-HMBC is a relative isotope shift, but what you got from 1D toxic is the absolute isotope shift. And from the isotope shift data we obtained here, we can clearly see that C2 and C4 has a larger isotope shift, and they will be connected to C5 directly. So C4 and C2 should directly connect to C5. So that is contradictory to our proposed structures. So based on this information, we can actually solve the structure. It's actually the real structure is this one. And if we map the COSY and HMBC correlations to the correct structure, so this is what we see. The COSY between H5 and H9 here is actually a 5-bond proton-proton coupling that as large as 4 Hertz. And also HMBC that used to determine that terbutyl is on this side of the n-butyl group is on this side of the molecule. It's actually a 4-bond and a 5-bond. It's actually a 4-bond and 5-bond CH correlations. So all these longer range correlations, but with a fairly large coupling constant, that leads to the misassignment of the original proposed structures. And with this, and the DFT calculation of these structures, both the proton-carbon chemical shift and the coupling constant, they all matched with the experimental data perfectly. So this is my last example. It's also like a side reaction, unexpected reaction. So this is a modified, this is a modified linear sugar moieties, and we want to deprotonate the alpha position and run derotation on it. But the deprotonation is not successful, and we observed another unexpected product formation. So based on the COSY correlations of this unknown product, we see a very long spin system, like all the way from C5 to C4, C3, C2, and directly to C1 prime. They all related by a decent coupling constant, the proton-proton coupling constant. But if you look at the original structure, it's very hard to get a byproduct that C1 prime directly linked to C2. So there's something could be wrong here, and then we obtain the isotope shift information. So what the isotope shift from i-HMBC obtained is here. So what we see is that there's a large isotope shift from proton 1 prime and proton 2 to the carbonyl C1 respectively, and this large isotope shift indicate C1 prime and C2 are directly connected to C1, and also the smaller isotope shift between C1 prime and C2 means that C1 prime and C2 are not directly connected to each other. So this carbon skeleton is wrong. The correct carbon skeleton is this C5, C4, C3, C2, C1, and C prime. So there's a C1 in between of C2 and C1 prime. With this information, we will quickly solve the real structure. So this is this oxytenone moieties with a 4-member ring and oxygen ether bond here. And so this 4 Hertz proton-proton correlation is actually a 4-bond proton-proton correlations here. Okay, so to summarize, so i-HMBC was originally proposed aim to solve like complicated proton deficient molecules, structural elucidation of the proton deficient molecules, and basically the aim was to develop a more sensitive 1-1 adequate analog. But now we find that it's actually it could be crucial for also for proton-rich compound, but with atypical coupling constant. And you can see in my examples, like the atypical coupling constant is quite common in our like daily the molecules like we work with daily. And the tiny isotope shift can be reliably measured using either i-HMBC or 1D C13 selective toxicity. So both methods have their own like advantage. And the most important thing is that by now we can like obtain this tiny isotope shift very accurately. Then we can use this isotope shift information to solve the structures and like build the carbon-carbon bond independently of coupling constant. So the experiment-wise, it's very similar. Like i-HMBC and toxicity is very similar to the conventional NMR experiments. The signal you observed is also related to the coupling constants because it undergoes the same magnetization transfers. However, the difference between isotope shift-based structural elucidation and the conventional coupling constant-based structural elucidation is that now, after we obtain the 2D NMR spectrum, now we interpret the bond distance by isotope shift, but not by interpret the coupling constant. So this eliminates a lot of unambiguities when dealing with unusual coupling constant, and this will give some like much more robust like structure elucidation workflow. So with that, I would like to thank all my colleagues. So this work is mainly by Yunyi and Misha and me. So Yunyi is here. Unfortunately, she cannot be present today, and all our collaborators. And thank you very much for your attendance.
And thank you, Xiao. So we'd be more than happy to take any questions if people have any inquiries or suggestions, comments, criticisms.
This is Krish. I have a question, more practical part of it. What can you comment on your proton acquisition, proton dimension acquisition, length and things like that, and how you considering this is an multiple bond, a typical processing? Can you comment on?
Yeah.
How you do that?
So we show that actually in our the first i-HMBC paper that you need to have at least 1 second of acquisition time on the time domain. So usually 1 to 2 seconds. The longer doesn't benefit much, and so right now I usually just use 1.5 seconds of acquisition time. So as a compromise between the relaxation and these things. But for small molecules, the relaxation is not much a concern. Like we tried even with 2 seconds of AQ, the signal is probably compared with like our traditional like 0.2 seconds of AQ HMBC. With 2 seconds of AQ, the signal is decreased by about a half. So it's still like acceptable sensitivity there. And so with that will translate it to like 2 seconds AQ will translate to 0.5 hertz resolution. And then when we process it, we digitize it 4 times. So it's 0.1 hertz. So that is still much larger than the accuracy we got. What we got is we can, if we got like 0.01 ppb accuracy, like or reproducibility during like measurement. So the accuracy was very it was very accurate. It's much higher than the digitization we use. So what we think is that because we do the line fitting of the peaks and there's a lot of like, I think there's a lot of like systematic error cancellations in our favor. So even with like 2 seconds of AQ, 2 seconds of AQ and 4 times of zero fitting, the resolution is still not quite reaching 1 ppb level, or it's probably about 1 ppb level. But actually, the real experimental data with what we got, we can get 0.01 ppb accuracy or reproducibility.
Because what about the processing side? I'm assuming you are not decoupling, you are not refocusing.
And we are not decoupling.
Yeah, so what can you comment on the processing side, and how does that affect your measurement accuracy?
So just HMBC, we use magnitude mode to process the data, and we just take the horizontal slice of the HMBC data, and then so you get the slice of the proton dimension, and then do line fitting.
Okay. Window functions.
Usually we just use the default Windows functions, like the in the Brew collaboration. I think it's just 90 degree.
Shifted signed up.
Yeah.
So you're pretty much weighing on the middle of you're weighing heavily on the half a second point in your acquisition. Your weighting function is pretty much a sine bell. So you are weighting significantly into the center of which is assuming you are running a 1 second acquisition. That's weighting to the half a second point as your maximum point. So have you played? My question really leads to, have you played with different window functions? Because by that time you may have a J coupling refocusing coming back, because by pre-precision it's going to refocus. Your J coupling, the active J coupling is going to refocus, and you are waiting on that, and that's going to affect your sensitivity, perhaps. I'm not questioning anything. I'm just curious as to the practical aspects of this experiment.
Yeah, we actually didn't try like different, like the only like Windows function we tried was like in some case the line is a little bit broad. We try to use some like line broad exponential line broadening to sharpen the lines. Yeah, we didn't change the shifted sum by all those things. We haven't tested that.
Okay.
Yeah, that's one of the things that we're doing now in our lab, is going through and kind of trying to screen through a whole bunch of different apodization functions to see what works best, and sort of a work in progress right now. We kind of got distracted on other things, but that's sort of on our high to-do list, and we made some progress with that when Simon Yellen was with us this past summer, and hope to close that out soon.
This is particular
report.
Sorry.
I was just saying, yeah, when we get all that done, we'll certainly give you a full report.
Yeah, this is particularly of interest to me because it brings back some memories of 40 years ago. I think there was a paper in the 80s by, I believe it was Kessler, of how the center of an anti-phase versus in-phase multipler component is affected. And by, I believe he was also talked about window functions. This is the time when we were, Gary must be smiling. We were working on long-range correlations by carbon observe. And so there are ramifications in displaying and measuring things out of a magnitude mode dimension, particularly if you are dealing with couplings that are evolving, and you are weighting it at a different part, weighting heavily on the later part of the FID, and that can affect how the line shape or the peak shape would be, and that will become very critical because you are trying to measure a parts per billion effects. And so that's why it just brings back memories. I have been out of all this for a long time, but so just curious. I'm becoming an old man. So.
Young at heart.
Young at heart, no. My heart doesn't think so, but that's okay. Gary, I'm sure Gary is still laughing. He's just sending me messages. So this brings back a lot of good memories, and there was a big discussion about how J-coupling evolution affects magnitude mode representation, because in those days that's pretty much more given that we tend to do magnitude mode in every dimension. Just watch out on that before you heavily weight on the later part of the FID. Your active coupling is evolving, and it's going from in phase to outer phase to in phase, and that will shift your center. And you are also dealing with potentially other couplings to that proton, right? Because you are also dealing with multiple quantum experiment in evolution dimension, and so you have JHH evolving during C13 evolution, and that's also going to affect how your C13 center would be, and so that you already addressed. You are taking the slice rather than projections, and that's an important one to keep in mind.
Mm-hmm.
Thank you.
Thanks, Chris.
Any other questions from the panel?
Yeah,
it's a very interesting experiment. I am very pleased to see some of these fundamentals revisited. So.
Yeah.
Yeah, for the magnet strength. So when I first developed this method, we were testing it from 500 to all the way to 800 megahertz. So they all works, and but for practical reasons, like actually, like all of the data I'm showing here is obtained from 600. We actually didn't use 800 for this work. And
how does your signal to noise affect your measurement? Signal to noise.
Oh yeah, that's a key issue, because we are using line fitting, so the noise will definitely shift the center. And so what we find is that like a 30-to-1 signal noise ratio is probably a safe threshold.
30-to-1 on the first increment. On the first increment.
No.
On the 2D.
On the slice.
Yeah, on the slice.
On the slice, okay.
Yeah.
Mm-hmm. And so far as line fitting, I think, at least in our lab, we've primarily been using the GSD functions in MNOVA. They work really nicely for finding this centroid of the peak. It also gives you a nice indication if you go through and turn everything on, see how the peak is simulated. You can actually tell if it's giving you an accurate picture or not. You can tell if you're getting yourself into trouble.
I'm just to be for the record, I'm not a big fan of fitting frequency domain data. So.
What a surprise.
It leads to too many dangerous zones.
Ron Crouch says he's had good success at 400 megahertz too, as long as the multiplet structure is not too terrible.
Andreas has a nice comment there.
Yeah. He says that he can sort F19 C13 isotope shifts from 3 feet away. So that's the new standard. We'll have to have a competition at the next ENC, see who can.
No, these are, I mean, these are really fundamental questions that I'm glad you're looking at these kind of stuff. For me, it brought back a lot of old memories. So, where we struggled.
If there are no more questions, I will close the meeting.
All right. Well, thanks, everyone.
Okay. Thank you, Thomas.
Thank you.
Thank you, Thomas and Israel.
Yeah, thank you. Thanks for the invitation and thanks for your time.